Hey there, everybody. Welcome back. We're on 13.3, partial derivatives of multivariable functions. This is in Anton's 11th edition of Calculus Early Transcendentals. Let's just jump right into it. Does a partial derivative imply continuity? When we did derivatives for single variable functions, the existence of the derivative meant continuity, but it's not guaranteed with partial derivatives for multivariable functions. And I really want to emphasize that. Existence of partial derivatives does not imply continuity. Let's take a look at an example. We have f of x, y equals x cubed y over the quantity x to the 6 plus y squared if x, y does not equal the origin, and then f of x, y equals 0 if it does equal the origin. We can do partial derivatives of this as x goes to 0 or y goes to 0. So the partial as x goes to 0, we use our limit definition, f of 0 plus delta x comma 0 minus f of 0, 0 over delta x. F of 0, 0 is defined right there as 0, so that goes to 0. And when we plug in, treat y as 0 there, we've got delta x to this. The top is delta x cubed times 0, which is just 0. The bottom is delta x to the 6th power plus 0, so delta x to the 6th. We've got this all over delta x. We can see this ends up being, we got 0 minus 0 on top, 0 over delta x. This is just 0. So the partial derivative with respect to x is 0. If we do the same for f of y, or the partial with respect to y, doing with limit as delta y goes to 0, same idea. F of 0, 0 is 0. We plug in x equals 0. So the top is 0. The bottom is delta y squared. Then we have our delta y on bottom. This just ends up being 0 over delta y, which is 0. Anything 0 divided by anything is 0. So both partial derivatives did exist. Recall from 13.2. Was it 13.2? It might have been 13.1. That with the limit along the line, I think it might have been 1. No, it was 2. I did it earlier. The limit along the line y equals x, the line was 0. Along y equals x cubed, the limit was 1/2. So it was not, it didn't have the same limit everywhere. So it was not continuous there. So the partials just don't show it. Okay. And we're not restricted to z equals f of x, y. We can upgrade it to having 3 variables in our function. W equals a function of x, y, z. We could do 4 variables where b is a function of w, x, y, z. So saying something like v subscript x is doing the partial derivative with respect to x of v, which means holding w, y, and z constant. The same thing happened with the delta epsilon proofs. I didn't actually say it. We can upgrade that to x squared, x minus x naught squared plus y minus y naught squared plus z minus z naught squared in that square root, and do f of x, y, z minus l. This all extends beyond just the f of x, y like that. Something else we'll look at in this section is implicit differentiation. The old way, remember when we did it before, we had the partial or the derivative with respect to x. If y was a function of x, this was starting off with xy equals 3, what was going on here. So we take the derivative of the left side, that do the product rule. I did the x1 first, it leaves me a y. I did the y1 second, I've got x. Y is a function of x though, so we say dy dx equals 0. That's how we did it in regular calculus. We're kicking it up a notch. We're going to look at the partial with respect to x and the partial with respect to y. Let's take a look at like doing it with this function right here. X squared plus y squared plus z squared plus 2xz plus 2yz plus 2xy equals 4. What happens when we take the partial derivatives here using implicit differentiation, because z is a function of f of x or x and y? Well, I'll do the x1 first. I'm going to hold y constant. So I'm taking the partial with respect to that. So what happens here? Partial with respect to x of x squared is 2x. The partial with respect to y squared is 0. The partial derivative with respect to x of z squared, we take the derivative 2z and then the chain rule dz dx. Just like we have the chain rule up here. Then we continue to go along. This one is a product of x and z. They're both related to x, so we got to do a product rule. I did the derivative of the first, getting 2z, and then I left x alone, did the derivative of z, and I have 2x times the partial derivative of z with respect to x. We do 2yz, only z is related to x, 2y is a constant, so I've got 2y dz dx. And then for 2xy, the only variable there is x, derivative is 2y, the right side is obviously 0. We're going to gather all the terms that are dz dx in parentheses. I subtracted everything else over. So 2x, 2z, and 2y move to the other side. I've got 2x plus 2y plus 2z in parentheses on dz dx. I divide that through, and you'll notice I end up with -1. So it's constant. That's kind of cool. The derivative of z with respect to x anywhere on that line is -1. Or on that function is -1. We'll do the same thing for the partial derivative with respect to y. So we're looking at that same equation. When we do the same process, doing the partial derivative with respect to y on this, we're going to get 2y plus, which comes from our y squared. X squared goes to 0. Y squared is 2y. Z squared goes to 2z dz dy. 2xz, the x part is constant, so this is the derivative of z. So I've got 2x dy dz. On the 2yz, these are both functions of it, y. So we got to do a product rule. We've got 2z when we do the derivative with y. When we do the derivative of z, we've got 2y dz dy, that should say. And then the last one, only the y is a variable with respect to y. So that ends up being 2x. This does the same thing. We can gather like terms, put them in parentheses, move everything else to the other side, and we showed that dz dy equals -1. Kind of cool. I think it's cool. You may not. Up to you. Peace.